Good morning, all of you. Welcome to the class, and let's resume where we have discussed. So let's review what we have already done. We have discussed binary tree operations, and last class we have discussed effectively level order traversal, and I asked you to think of iterative in order or pre-order or any depth traversal. So this is what we have discussed already. Let's have a quick review of demonstration of the code and have a look on those who need some help. Otherwise, code was simple. I'm sure some of you must have easily done that. So this is a level order traversal coding. Here, some changes in the create also I have done. Just to show you that create itself, when I said you to have a create tree to have a meaningful message, same thing is easily achievable via create function itself, where I have said that when I gave the choice, immediately at that point also I can have a printf statement, because at that time root is accessible and I know which side I'm going. So I can directly write here printf and then make the call, recursive call to the create function. So no parameters needed, still the same thing achieved. Similarly for the right side, just give a printf in the is this call itself, and then recursion starts. So that saves the headache of saving extra parameters or sending extra parameters. And for the root case, you can have a special case that if root is being created at that time itself, you can have the corresponding message given and accordingly done like that. So these two extra printfs into this particular situation, and accordingly this printf plus this printf just before the recursive call can help me in achieving the same work which I achieved via create. So simple method, but create 3 I specifically asked you so that you learn parameter passing in the recursive calls, and like for ancestors, etc., that could be useful or needed in some other situations also. So create 3 also must be practiced, where side and roots parameter or roots data or root node is supplied to the next recursive call. Now coming to more important aspect, that is my level order traversal. So I'll just show the level order traversal. For level order traversal, I will need insert queue. I'll need a delete queue. So insert queue, I have an array tree queue as an array of pointers, rear being maintained as a initial value -1 or whatever node which is to be inserted. So I have that correspondingly array declared, and then accordingly that is here you can see that when we have in the main the corresponding array declared as there is the level order traversal. So I think I have declared somewhere. Let me see where are those variables declared. Could be into the level order traversal itself. Yeah, here. So I have here array of pointers. So tree queue is array of pointers declared. Then I have front and rear as -1. So it's a normal queue, not circular queue. And then accordingly, you have your insert queue, which we already know how to implement, delete queue, how to implement, queue empty, how to implement, and then using level order traversal going one by one. So if root is null, nothing to be done. Otherwise, I just insert and then a loop till queue is not empty, delete queue, print its data, insert the left child if it exists, insert the right child if it exists. And that's it, nothing else. So line-wise, I'm not showing the code. I want you to try in that. Similarly, level order traversal using a queue as a linked list, you should try. So having stopped here, let's say now based on this, I can easily resume and go further. So now going further, let's extend the concepts of a binary tree for some useful more concepts. So additional concepts, specifically related to some concepts related to searching. For example, search in a binary tree you have implemented already, but for the search in the binary tree, just see how many nodes or what is the time complexity. Of course, I am talking of a time complexity not in the best case, because best case means on the root itself, the data was available. So best case time complexity is order of 1. That is not a doubt. Other cases, I'll say average case or worst case. A worst case could mean even unsuccessful cases also. So if I have unsuccessful search, then also it will be worst case situation like that. Effectively meaning you might not know how to calculate a time complexity for recursive functions because that was recursively written. So the process is how many nodes need to be traversed in worst case or average case or unsuccessful. How many nodes to be traversed. If you can find that, that will straight away tell the corresponding logic. For worst case or for unsuccessful case, not at the root itself, obviously, how many nodes to be traversed. If a tree has n nodes, how many you will need to traverse? So answer is straight away all n nodes. Only then you will be able to conclude unsuccessful case. Similarly, let's say average case, I mean not the best case. So you are going up to the last node or somewhere near the last node or somewhere in the middle. So you could say approximately, let's say n by 2 nodes. Say on average after half time or after half node comparisons you are able to get. But all this effectively mean this complexity is claimed to be order of n because n its traversals will mean order of n. N traversals of n by 2, that is always, we don't care about the 2 etc. to be written, it is always said to be order of n. So order of n by 2, or if you write as 5n, so that is always a time complexity is order of n by 2. We don't write n by 2 at all. So time complexity is order of n. It means all nodes need to be searched effectively on average, or loop is equivalent to all nodes comparison. This can be improved by having the binary tree working in a better manner. And we change the concept of a binary tree to become binary search tree. And the search becomes faster and more efficient if I have a good tree, a balanced tree available. So my first search can be fast. So binary search tree, effectively it will mean that if I have a value here on root 30, then the rule will be the left subtree will have all values less than 30. And right subtree will have all values greater than sub 30. So that is first thing. So my all values have a differentiation. Left subtree always supposed to have value less than root, and all values in the right subtree are having values greater than 30. Not only that, so this is first condition. Second condition is every node of this subtree of a BST follows this rule. Follows this rule means the left side value to be less than root and right side's value to be greater than root. So this rule is applicable on every node. Indirectly, I'll say recursively, I mean every node of the tree is also BST. So when I say BST, this rule is applicable on the values as well as every node following this rule. Meaning, if this is 30, let's say this is 20, say this is 60, then this side value can be greater than 20, but less than 30. So this value could be 25, this value could be 28, this value can be greater than 20, but less than 30, obviously. This side less than 20, so maybe 10. This side greater than 20, less than 20, greater than 10, less than 20. Let's say 50. This side can be anything less than 10. 15, like here. The value can be in between any value 16 to 19, but any other value will be incorrect. So this side, any value could be, let's say 70. Here, any value in between 61 to 69. These all values are greater than 30. These all values are less than 30. Same rule applicable on this node. All values on the left side are less than 20. All values on the right side are greater than 20. All values on the right of 60 are greater than 60. All values on this side can be less than 60 and obviously greater than 30 because that is a condition already mentioned by this. So this becomes my BST. Now, if I know this BST, so just recall when we differentiated a tree versus binary tree, at that time I have pointed out that in a binary tree, it will be possible to have different properties for left and right children. For a tree, all children are treated in a similar manner, but in binary tree, we are using effectively for different properties for left child or right child. So here we have that condition, and that's why this is being used. Going further, let's now understanding this. So this is a kind of sample BST. Here I have, let's say 20. This side I have a 60. Let's say here I have 10. Here I have, let's say 25. This side I can have, let's say 23. This side I can have 70. This side I might have, let's say 50. This side I can have 45. This side I can have, let's say 80. And maybe anywhere, anything. For example, here I can have 65. Here I might have 62. So all this is a valid BST. Now, this is satisfying all properties at every time. Now I say search can be made much more faster. And reason being, once you are comparing the value with 30, let's say I want to search for value 43 or value 64 or let's say value 65, anyone. So let's see one by one. 43. I come to 30, straight away 43 is greater than this. It means search in right side only of 30. No left side to be searched. Then you reach to 60. Guaranteedly need not search this side. You will say search this side. 50, less than 50, 43, search this side. 45, less than 43, 45, left side should exist, not exist, unsuccessful. 64, similar process, I will reach to 64, 62, 65's left side, 64 can exist, 62's right side can exist, not exist, unsuccessful. 65, 30 you compare, 65 is greater, search in the right subtree. 60, 65 is greater, search in the right subtree. 70, 65 is lesser, search in the left subtree. 65, found. So effectively, this is way it will be able to work well. So effectively, if you say, even if you talk of unsuccessful search, the steps have reduced because every time your one side gets reduced. So in unsuccessful cases, how many nodes you will need to be traversed? On every situation, effectively, it will be equal to height number of nodes. For example, if I was searching for 64, maximum up to this height you will come. If I was searching for, let's say 20 or some value like this, I will say 21. Even in worst case, I will reach up to this and then conclude. So effectively, height number of times. If I have my tree is, if a BST is balanced, more or less. Balanced will mean that good mix of left and right children exist at every level, and there is no missing left and right links frequently. So if the tree has total n nodes, for a balanced tree, effectively, height is going to be approximately log 2n, because each node to have left and right children. If almost all nodes have and the tree is distributed properly, so I have distribution to be both sides, distributed well on both sides, then my tree will be quite balanced. And then, of course, I will say the height is log 2n. So my searching will become order of height times. And if tree is good balanced, this becomes order of log 2n, much better than order of n. So I can achieve good thing. Of course, if my BST is not balanced, that could mean that it is skewed in one direction. For example, this is also possible that such a tree exists. This is still a BST, but it is a kind of unbalanced, or I normally call it as a skewed BST. No right children, so effectively n nodes mean height also becoming n. This becomes an unbalanced tree and obviously not a good solution. This is effectively a kind of a linked list, singly linked list. And obviously the advantage of balanced height, etc., will be lost. So, of course, we will not prefer to have such kind of a BST. Balanced BST, if I have, I can save time in searching. So, now, assuming that you have a good BST and BST exists, we are supposed to implement, first of all, search. So let's try to see how search logic should be implemented. So search now, of course, can be recursive also, because I can search either on the left side or on the right side based on the data. Recursive implementation is also easy, but iterative is also equally easy, because you will find whatever recursion achieves, same you can easily implement without recursion also. And so then iterative becomes much more easy. For example, let's say I have on implementation now. For example, I said I start with 30 and I am searching for value 25. So 25 being searched will mean with 30 comparison, I will be able to decide to go to the left side or right side. Then change your current pointer to left side. Again, from here, you can change your current pointer to 25 and 25 you will be able to match. So no recursion needed. I can just keep on changing my current pointer. Either I get the element or I will reach to null. That's it. So that can become a straightaway logic for the corresponding implementation. So let's think of writing the code. So if I say, let's say search into BST. So I write function name as a search BST. What parameters I should have, what return type I should have. Parameters, you need your BST root. So I'll say root, or in this case, let's say I write star BST node star just to differentiate with a different name. What else you need a parameter? For searching, you need the tree and you need the value which is to be searched. So the val which you need to search, you will supply. What it should return. We have already discussed that node pointer should be returned, so that wherever it is found, that node pointer is returned so that we can use it for any further operations. So now, first case, always think if I have the tree as null, special case. If BST equal to null, I can directly conclude what is the answer. BST equal to null, element not found, effectively I have to return unsuccessful data. Unsuccessful means because node star is to be returned, I can return null. I might write here else, if I write here else, I need nesting to be done. If I don't write, I can still write the code here. It is still equivalent to else, because the return statement is already written. So it will stop the code. Now what? Effectively, I said every time what I have to do, first compare with the root data. So I will take some current node so that I don't change my BST pointer anywhere. BST remains to the root and I take my current node, current equal to BST. First thing, if my val is equal to current node's data, what is you can tell? Data found, nothing else to be done, work is over. Work is over means you can return the node. Which node to be returned? Yes, current. I have this current node ready, which has got the data. Done. Else, even if I don't write else, it means the same thing. But now, else writing becomes much more meaningful because I want to compare the value. Now, if the data, for example, I'm saying 30, this side is 20, this side is 60, and this side is 25. Here I have 23. So let's take a case, search for 25, or later we will take search for some value 85. So 25 exists, 85 doesn't exist. We will take this case. So 60 has 80 here and some more data, and 25 is this and some more data, wherever. So this side, but it is null. Let's here it is ending. Now, corresponding to comparison with 30, first of all, I'll say if 30 and 25 not equal, then I can decide 25, if at all to be found, it has to be searched into the left subtree. So recursion visible. Without recursion, I say, don't have any problem. Let's bring your current node to the left side. So I'll say if val is less than current arrow data, what you can decide? Your current should shift to this, and next time my comparison should be done with this node. So current can become current arrow left. Similarly, else guaranteedly means that val is greater than this. So my current node should become current arrow right. Now, I was on 30. My current node has shifted to the 20. Same process to be repeated. Again, compare 25 with 20. Either you will find the node or you will change your current node. So you have to loop. Till what time you should loop? Either you will find the data. Find the data means effectively this will terminate your code. So my while loop can be simply there. And for long, how much long I should continue? Might be, let's think of case 85. With 30, you will compare. You say search into the right subtree. So your current becomes 60. You say 85 is greater than 60. You will say current should become this node. With 80, again, you say shift to the right side. You reach to null. Guaranteedly, the solution is ready. Unsuccessful case. So that simply means I can have while current not equal to null. So this was here. While current not equal to null, I keep on repeating and done. Almost over. Don't forget to have a return statement, because once your function is over, return statement is must. So what I should return now? Unsuccessful only I will read. For successful cases, this return statement will work. So coming here means return null, or you can also write return current, because current is also null. So both are okay. Even if you write here return current, that is also fine. In that case, even you could write here a break and then come here and directly return current for all situations. Otherwise, reaching here in this situation, if you have used here return, guaranteedly means that it was unsuccessful case. Null should be returned. So that becomes a straightaway search logic. Then next comes how your BST will be created. So now your creation logic has to be handled. So I say in this case, it's not like a simple creation, because we have all values to follow certain restrictions. We can't have anybody to be left child or any right child. No, it's not there. For example, first value comes as 30. It has to become root. There is no choice. As soon as it is root, each value to be put inside this has a guaranteed one simple position to be inserted. that position will be decided by the value itself, because the value has to be on the left or right side. Now 30s, like if I say now after 30, I want to insert a 10. Even if I was creating and after 30, 10, I can't say 10 can be 30's right side. It will be incorrect. So the only choice is 10 has to be here only, because this side was empty and I could easily do. Now let's say I want to insert 5. Now 5 cannot be anywhere else, but a free space has to be found, and that free space also will be on the left or right of somebody as per the value itself. Now let's say I want to insert 70. 70 to be inserted. 70's right place is this only. Then let's say I want to insert 50. Of course, one way could be that after 50, now 30, 50 should be somewhere here, but that insertion will mean further all trees to be shifted and so many other different complexities. 70 already might have some data. For example, now I say insert 70 and then 50 to be inserted. So I'll say 50 ideally should come here only, greater than 30, less than 70. It has to be 70's left side, 30's right side. This is the only place. Let's say insert, say I want to insert 8. 8 is less than 30, but can I put 8 here? No. First thing, already linking is there. Secondly, if you try to put here 8, the remaining relation will become wrong. Maybe you think put here 8, no. Maybe you think somewhere like this. So easiest choice is keep on going to do the insertion, and once you reach to the last node, then insertion will be there. So insertion is easy to make new node as leaf. And making it as leaf makes the things simpler. Keep on finding the correct place, find the correct place and correct empty link, and at that place put this node. For example, 8 to be inserted. I say 8 has to be 30's left side, but left side is not free. So I say go further. 8 has to be 10's left side. Left side is not free. So go to 5. 5's right side. 5's right side, because the 10's left is guaranteed. I have already come. 5's right side is free. So I will be able to insert 8 here. So this way, I'm able to do the insertion at this place. So I can do the correct empty link insertion at this particular point. And I can use this value for the corresponding situation. This was meeting. Okay. Fine. Yeah, so I can find out the correct empty link position and insert my 8 at this place. So this way the logic can continue and it becomes easiest to implement. So again, you can see insertion can be iterative as well as recursive. Both are equally easy, because similar logic can be made for this. But one thing is clear, making it leaf could make the things easy. And if I say making it leaf, there will be exactly one position only possible for the insertion. If it is to be inserted as a leaf, for that particular value, exactly one position exists. I will reach to that position and insert at that point. Let's talk of implementation finally. For implementation, the logic will be again simple. The logic is closer to my search logic. The only thing is, in search, effectively, I have to reach to a situation where we reach to the null node, reach to the last location, null direction, or effectively leaf position. And at that point, you have to do the insertion. Meaning what? For example, I said I have to insert 8. I am at 30. This side has a 10. This side has a 5. And 8 to be inserted. 8 to be inserted, I will search for 8. Search for 8. 8 is less than 30. Search for 8, less than 10. Search for 8, less than 5. Let's say I have here 7 also. Search for 8, greater than 8, right side. This side is empty. So 8 has to come here. So the only thing is, in search, your current becomes null, and then you could have the correct position found. But once you reached to null, insertion will not be possible. So just before current, my previous link should have been stored, and I know previous, then I will be able to say previous arrow right equal to this current node. So I need just with the searching logic, one extra pointer previous, because you will reach to the null location and this. Secondly, unique values only will exist into the tree in BST. Duplicate values don't exist. If I want to handle duplicate values, special logic will be needed if you want to handle duplicate values. But otherwise, duplicate values will not be handled by default. So for that, you will think to make special logic. But by default, we assume unique values. So if the value was already existing, for example, I wanted to insert 7 or insert 5. You found 5. So already existing cannot be reinserted. So then you should be able to conclude that it can't be inserted and takes suitable logic or whatever. So now let's try to write this function, insert into BST to be written. What parameters should I have? Obviously, same as the search situation, I need the root, or I'll say star BST, and the value to be inserted. Assuming value is to be new, of course, if it is already existing, we will take special case. Return what? The updated BST needs to be returned. Even in empty BST, insertion will be attempted, and then your BST root will change. So what to do? First thing is, always the new value is to be inserted as a leaf. So you have to effectively create your node of leaf. For this val effectively mean that you have to do malloc. So I will say, let's say, take some temporary node, temp equal to malloc, temp arrow data will be the corresponding val. And because this is going to be always a leaf node, its left side also to be initialized with null. Right side also to be initialized with null. So this work done. For example, I wanted to insert 8. So I'll say or let's say insert 3. So obviously I will need one node which is having value 3, this side null, this side null, and this will come somewhere linking. First, so this is your temp point. This node is ready by this state. Now I have to find a place for 3 to be inserted. And effectively through unsuccessful search, I have to find a place. So that means more or less my search logic has to be written. So I will say current equal to BST and accordingly go. Take the special case first. If BST is null, BST is null means first node being created. So obviously my current node will become the BST, or temp will become the BST. So I can directly say return temp, because that will become the BST, and it has already the children as null. Things are ready. Even if I don't write this statement, this is going to be a special situation and it will handle that. After this, BST pointer or root pointer will never change. Once root is freezed, root will never change because all values will be inserted accordingly. So BST null, return temp. Now, otherwise, I will say, let's take current equal to BST, and then I will have a while loop, while current not equal to null, all that same logic whichever we have written. If data was equal, now that earlier it meant a successful case, it means wrong insertion being attempted. This is not permitted. So you can give this message, and in that case, if you want to return something special, say return null or whatever you want to do, that situation you can handle. Else, your current will keep on changing. Current will go to current arrow left, or it will go to right as per the data available. The same logic which we have already written. The only thing is, once you come here, now current has become null. Where to insert? I want to insert somebody. I need the previous node. So I will say, initially, before shifting my current, I will always have a previous node to be assigned as the current node. So this will always maintain the previous node. Initially, 30 is my current, so previous also becomes 30. From 30, your current shifts down because of this left side. Say I was inserting 3. Current shifts to 10, previous is 30. Next iteration, previous equal to current, so previous comes here. 3 to be inserted, 3 compared with 10 means current again to come down to the left side. Current comes here, previous is 10. Loop again, we have not ended, previous becomes current. Previous again comes here. 5. Data compared, if 3 less than 5, yes, go to the left side, current will change. Current will become null, current becomes null. Now, current becomes null, loop over. My previous pointer is available, which is pointing to 5. Now I can use this previous pointer, and effectively I have to say previous arrow either left to be equal to temp, but not always left. It could be right also, because maybe I was inserting somewhere, let's say 5 has something, and say this node didn't exist, this node didn't exist, I wanted to insert 6. Still, it could be the same situation. So which side I should link? How to decide? So either I should have some special logic insert initially storing which side I was moving, but I say not need, I can compare with the data itself. The value itself tells whether the temp is going to be the left link for previous or right link. So if value was less val or temp arrow data, if it is less than previous arrow data, that decides whether this node should become left side or right side. So I can think to compare, if val less than previous arrow data means if a 3 is less than 5, then this node is supposed to become left child. That will mean then I will write previous arrow left equal to val. Else, obviously, previous arrow right to be equal to val. So this code can be directly used at this situation. Instead of writing this, I will write this. What else? The work is almost over, but don't forget to write a return statement. What to return? The BST pointer, the root pointer. Even if it has not changed, because I have written node star, return is a must. from the main, how the call will come. So I have to now make the call from the main by initially taking, maybe let's say I have node star some BST1. Initially, I will take it null so that insertion into null tree is still working, and every time whenever I call, I will always write BST1 equal to insert with the current BST1 and whatever value. And whatever loop you needed or whatever choice-based repetition you needed, whatever you want to do, you can keep on inserting. So if you want to create will not guarantee any value to go on left or right side. Create is equivalent to insertion. Maybe insertion multiple times. That straight away gives you a choice that you can keep on creating as many times as you want. Every time the node has to go exactly at one position. So your create of many nodes will be equal to saying insertion multiple times. And you just call iteratively or many times that, loop that, and then it is done. Not only that, deletion will also be needed now. And deletion is more complex. Insertion was easy because insertion was done only at the leaf place. I reached to that position and then I was able to delete, insert. But let's say here I have 30, here I have 60, here I have 50, here I have 70, and some more values like now. If I say delete 60, now this deletion is not going to straight away be easy because I can't have this deleted, then what will happen to this node and this node? At most 30 could be linked with one of them, but other side will have a problem. So deletion will have many different situations. Some of the situations could be easy to handle. Some situations could be difficult to handle. So deletion we will discuss next class, and we will talk of those situations, and then I will discuss what is delete logic. But of course, insertion was easy because this made the things at the leaf level. And other nodes were not disturbed at all. Other existing nodes were not disturbed. Deletion could disturb other nodes also. So other rule and relationship established simple. So having said that, I think we will just go toward the final discussions. The one beauty of this is all traversals still can be done to verify your results. You can have your in order, pre-order, post-order, or your level order. All you can use as it is, and without difficulty, they will give you correct output. But in order has a special advantage. In order meant left data right. And because I know now that left side values are always less than data and right side values are always greater than data, hence in order traversal will give me the sorted or ascending order sorted listing of the nodes. So my BST in order will be quite helpful to confirm and check your results in easiest manner, that just do the in order traversal and your ascending order sorted output will be generated. Having said that, let me now just wind up. So I will say homework, implement first search BST, second insert BST, and of course check that with traversals, but those are not to be implemented, they are straight away easy. So I will say implement iterative version, which we have just coded almost for these. Good students, should try the recursive versions also. So for good students, recursive search BST and recursive insert BST also should be attempted. So with this, I will stop and wishing you a very successful preparation and good examination of your second tests. Bye-bye. All the best to all of you.